right. Good morning, guys. I hope you're doing well. I hope you had a great weekend. So I wanted to pick up here with the sample questions from our acid-base equilibria discussion. Does anybody have any questions before we get started with that? Okay. So I had asked you to take a look at these and see what you thought of them. I'm going to walk through the way that I would approach all of these, and then we'll get into the next lecture. And if we get time, we'll start titrations. The last thing that's going to be on exam 1 is that titrations lecture, which we will either finish there's no way we won't finish it by Wednesday. And if for whatever reason we don't, then we'll talk about moving the test. But I don't see that there's any reason that we wouldn't finish it by Wednesday. We may finish it before. That's the last thing that would be on exam 1. Now we will start materials from exam 2, just because I find that students do better with a little extra time in between. So I will give you that if I possibly can. Okay. And just in case anybody has any questions, I will leave the test opening date for Friday, regardless of where we are, because people may have a situation where they can't take the test after that. So I will leave that as the opening date and extend the due date if necessary. Okay. All right. So let's start with at 300 degrees, the pKw of water is 11.34. First question I ask you is, what is the Kw of water at this temperature? Well, if we think about the relationship between pH and pOH and all of the rest of that, we know that what happens when we go from the P something to the non-P something is to take 10 to that negative whatever it is. So if I have 10 to the negative pKw, that should give me Kw. It's the same relationship. And so my value should be 1 times 10 to the minus 11.34. So instead of 1 times 10 to the minus 14th, at this temperature, it's 1 times 10 to the minus 11.34. Okay, so that's my Kw at that temperature. The sum of the pH and the pOH at that temperature is going to be equal to that 11.34. Because again, we have that 11.34 is equal to pH plus pOH. It works exactly the same way as it does when the value is 14. So that's what that sum would be. What's the value of pH at that temperature? Well, if I'm looking at the two, if we're in a neutral situation in water, the pH and the pOH are equal to each other, and therefore they're both 7 because the overall is 14. So we're going to take that 11.34 and divide it by 2 to get what the value of pH and pOH are. And so each one should be 5.67. And so if I add those two together, that would give me that 11.34. Okay. And because we know how to go between the pH and the H3O plus, again, that's 10 to the negative pH. And so that's 10 to the negative 5.67. The same would be true for the pOH. Because we're in a situation where everything is equal. So I'm hoping that that will follow from the logic of how we got to all of the values that we use under normal circumstances, i.e. when the value is 1 times 10 to the minus 14th. This is just an extension of that. And this reminds you that at any other temperature, that value has, or the K has a different value. So that's what we're looking at there. Does that make sense? I'm going to assume yes if I get no questions. Now, it says to use the acid scale to tell me the strongest, weakest, and 2 of the 2 in the middle acids and bases, and rank them according to the chart. Okay, so I know that I have one of those charts in a couple slides. So I'm going to go Look at that. So this is that chart that we were looking at here. And so the strongest acid that's listed here is HCl. So I have HCl at the top. The weakest acid that I have is CH4. And it just says to pick 2 in the middle. So I'm going to pick, for kicks, HF, because he's right here. And then I'm going to pick H2S. And so if I wanted to put them in order according to the chart, I would move my CH4 to the bottom. Because that's how they appear on the chart. Okay, so that's what I was talking about with that question. When we talk about our bases, our strongest base is this one down here, CH3 minus. Because remember, this one is reversed. The weakest is that Cl minus, which really has no activity. And 2 in the middle. Doesn't really matter which 2 I choose. I'm going to choose NH3, because he's right here. And then I'll choose CH3 COO minus. And again, as long as they're in the same order as they are in the chart, that's what I'm looking for. Okay. So questions on that one? Sorry. I have a 0.035 molar HNO3. I want to know the concentrations of the H plus, the OH minus, the NO3 minus, and the HNO3 at equilibrium for this species. I also want to know the pH and the pOH. So for HNO3, I know that this completely dissociates because it's one of the strong acids that's listed on that table. So I see it right over here on this table. And so it's a strong acid, it completely dissociates. That means that I have an H plus equal to the NO3 minus, and that's equal to 0.035 molar, because that's what I was given. So I know that those are what I'm looking at there. If I want to talk about what's the concentration of the HNO3, that's equal to 0, because it's a strong acid. So I have none left. If I want to know what the OH minus is, I can do that in 2 ways. I can either take 1 times 10 to the minus 14th divided by the 0.035 molar, or I can find out what the pH is, which is equal to the negative log of that 0.035. And what do you do? Oh, that's fine. Which gives me 1.5. And then my pOH is equal to 14 minus the 1.5, which is what, 12.5, I think. And then if I wanted to find the OH minus, I could also take second 10x negative 14 minus 1.5, which gives me that value. So either one of those will give me this same number for this OH minus of 3. Technically, that should be just 3 because I lose 1 sig fig. So 3. Oh, no, 3.2. I gain 1 going this direction. So 1.3.16. My sig figs are terrible today. instead of -13 because I gain a significant direction. So there we go. Cool with that. So that's the pH, POH, H3O, H plus, NO3 minus, HNO3, and the OH minus. So that's everything that it asked me for. All right. I wanted to do the same kind of thing for the MgOH2 that's next. The thing here that's a little bit different is I have an MgOH2. And so my concentration for the OH is going to be 2 times at 0.043 because there are 2 OHs that come from that. And so I take that 0.43 times 2, gives me 0.86. And that's equal to the OH minus. Since it completely dissociates, it is oh, actually, it's not listed in that. So I don't know any of those. Go me. So it's not listed here as one of our strong bases. So I don't actually know what any of those concentrations are. I know it's less than that, but I don't know exactly what. So I apologize for that. And because that's all I know at this point, I don't know anything further about how to solve that because it's not in that strong list. Then I don't know how to solve for any of those other values. Does that make sense? I had forgotten I had put a weak in there and not a strong. So sorry. Now, one last thing that it asks. It says for each solution, what is the PNO3 and the PMG? Now, I don't know what the PMG is because I don't know what its concentration is. But the P for the NO3 is just the negative log of the NO3 minus. And so that's going to be 1.5 as well because it's the same value as what I have for H plus. So it's the negative log of the NO3 minus. Okay, when we do those P's, we always lose the charges that are there. So it's just the negative log of that NO3 minus concentration. And so it's 1.5. Okay. Questions about any of that? This always starts with knowing whether it's strong or not at this point. We'll get to the rest of it. Okay. Didn't actually need that. Here's the next page. Sorry. Okay. When we talk about these type of charts, we're again looking at, are we talking about strong acid, strong base, that kind of thing? So when we talk about HI, that is a strong acid. It's in that list. So it is a strong acid. If it is a strong acid, and I know that this is a 0.1 molar solution for that species, then I know that the concentration for those guys is 0.1 mole. Okay. And that's an H plus that I'm looking at that I get from this species because it's an acid. Does it fit the definition of an arsenous acid? Yes, because it's a proton donor. So yes, it fits this. Does it fit the definition of a Bronsted-Lowry acid? Yes, because it's a proton donor. For Lewis, no, not necessarily. Okay, so we take that out of there. By definition, it is not that. We talk about HBr. Br is also a strong acid. So we still have a 0.1 molar concentration. I know that it's an H plus donor based on the structure that I have here, and therefore it's an arsenous acid and a Bronsted-Lowry acid because of that. It does not fit the definition for the Lewis acid or base. Okay. When we talk about H3PO4, I do not see that in my strong acid, strong base list. So because I don't see it there, I can assume that it's weak. Now, is that a good assumption? No, not really, but we're not considering the H3PO4 part. The reason that we don't is because it's complicated. Okay, so that's why it's not in that list. So because it's not there, it would be fine if you assumed that it was weak. Not a big deal. It is an H+ donor to whatever extent that it does it, and therefore it does fit the Arrhenius acid definition and the Bronsted-Lowry acid definition. We don't know anything about whether or not it is a Lewis. It is not a requirement that it be a strong acid for it to fit those definitions. Okay. We talk about HClO4. That is a strong acid. We know that this is a 0.1 molar for that. We know it's an H+ donor. We know that it fits the Arrhenius definition because it's an H+ donor. And we know that it fits the Bronsted-Lowry definition because it's an H+ donor. Okay. Our acids are typically pretty boring. They're either Arrhenius and Bronsted-Lowry or Lewis. So one or the other. When we talk about BeOH2, okay, so BeOH2 not listed in the list of strong bases. So I can assume that that is weak. When it does dissociate, it does give me an OH-. And so it fits the Arrhenius base definition because it generates an OH-. Okay. Now, can it also be a proton acceptor? Well, yeah, okay, but that's a secondary step, and so we don't list that. All right. CaOH2 is listed as a strong base. And therefore, we know that since this was a 0.1 for the solution, my OH- is a 0.2 molar. It is an OH- donor. And therefore, it fits the Arrhenius definition, not necessarily the Bronsted-Lowry, because while it can pick up from that OH, it's not necessarily doing so in that first step. So when we talk about an RBOH, okay, that is listed, is not listed, although it should be, is not listed in that table, so we can assume it's weak. And I say that because all group 1 metals should be strong bases, but it's not listed there, so I'm going to say that way. So OH- donor again, and that makes it an Arrhenius base. Okay. Now we get to this CH3NH2. It's not in that list, and so I know it's weak. It is definitely weak. It is not an OH- donor. Okay. So it generates OH secondarily by reacting with H2O. So I generate an OH eventually, and so I would list that as an OH, but it doesn't do it by the Arrhenius definition. It does it by the Bronsted-Lowry definition. So it can accept a proton. It becomes a CH3NH2+. Okay, so it's a proton acceptor. Right? Now, it tends to do that by using that lone pair, and so it typically falls into the Lewis base category as well. But it is primarily a proton acceptor. Okay? So either one of those is acceptable. You don't necessarily have to list the Lewis. It's not as important that you do. Okay. So questions about that?
Is a chart like this, like that we have to fill out, going to be on our exam?
Yeah.
Okay, so I'm confused because in some of these you're like, it's a secondary step, so we don't list it, but for the C3NH2, would it being a Bronsted-Lowry base be like a secondary condition since it has to react with something to get the O?
It's so the primary thing that it does is to pick up the proton. So the Bronsted-Lowry pickup of the proton, that base definition, is the primary. The definition of the OH- generation is the secondary step.
I'm just confused because in some of these, like for certain molecules, you said like we're not listing secondary steps like for the bases, but we did for the last one. So I just like
Yeah,
on
like
the
the
example, like,
BOH2. Yeah, I had the same question.
So,
Because on BOH2 you said it didn't really matter, or like because it was a secondary step, so you don't consider that.
well, no, the BeOH2 definitely
Mhm.
donates an OH minus. It's just not a strong base. So it always donates that OH minus. It's just we don't know what to what extent it does.
Okay.
So that's slightly different. When we talk about the CH3NH2, the thing that it does is to pick up a proton. So its definition, by Bronsted-Lowry definition, is that it picked up a proton. So it is that's the primary thing that it does, is to pick up that proton. The secondary thing that it does is to generate the OH minus. And so since I have this list right here that's asking, basically, is it an acid or is it a base? That's really what that's about. It is a base because it
Right.
eventually generates the OH minus. This part, this column right here, doesn't matter if it's first or second step. This definition over here is about first or second step. This one, and this one.
Okay. So
Is that
if it's not primary, then it's not that. Like if
correct?
even if it's like a secondary step, all you worry about is like the initial one.
For these definitions over here, yeah, the Arrhenius, the Bronsted-Lowry, and the Lewis. That's correct. And the way that I typically put this on the test, just so you know, is it says acid or base rather than H plus or OH minus.
Okay.
Because that is less confusing.
So most of them are like not Lewis based. Like why is that not so prominent?
Because it's mostly what we see for organic components, and we
Okay.
don't talk a lot about them in this class.
Gotcha. Okay.
But it is something we have to be aware of, because as we move into the weak bases and especially the weak bases, that's primarily what you're going to be looking at.
Okay. Mhm. Thank you.
So does that help?
A little bit.
yes, thank you.
Yeah, because I again understood as we were going through class that this was not the best way to define it as the H plus or the OH minus, meaning acid or base. So that's why on the test it doesn't appear that way. So I hope that helps. Anything else?
I think we're good.
Oh, go ahead. Oh,
I said I
okay.
think we're good. Yeah.
Okay. Now, for this, which is the stronger acid? HF or CH3COOH?
The HF is a weak one,
Well, they're both
isn't it?
weak acids, but which is the stronger of them?
Um, hold on. HF or what? I'm sorry. What was the other one? Oh, HF or C.
CH3COOH. So we're comparing this
Uh,
right here to that right there.
HF is stronger since it's
Yes,
above on the list.
right. Because it's higher in the list, HF is going to be the stronger of those two acids. When we talk about HCl, which is here, versus H2SO4, HCl will be the stronger acid because, again, it's higher in the list. When we talk about HNO3, where's my HNO3? He's right there. And then we're talking about NH4 plus, which is down here somewhere. Since HNO3 is higher, we would rank that higher. So again, HNO3 is higher, HCl is higher, and HF is higher, because I felt like writing all the ones that were higher first. So when we
Makes
talk
sense.
about stronger bases. So our stronger bases are down here at the bottom. Our F minus, because it's lower than the Cl, is going to be the stronger base.
I mean, it makes sense because the F is like the weaker acid, so it's a stronger
Correct.
base.
That is correct.
Okay.
We talk about O2 minus is here, and our OH minus is way up here. So our OH minus is the stronger of those two. And our PO4 3 minus is this guy right here. And our CH3CO minus is here. So this is the stronger of those bases. And again, that's just based on where they are in the chart. Cool with that?
Mhm.
Wait, is PO4 not the stronger base?
And I did that backwards. I'm so sorry. I'm so sorry. Yes, because it's, no, wait, no, because it's the one that's, yeah, it is lower. Never mind. So yes, it is the stronger. Sorry. So cool with that. Thank you for catching it.
Yes.
All right. And that is everything I had for that particular lecture. So questions on what we talked about there? Anything? All right. So now we've gone through a lot of the definitions. We've reminded ourselves of a lot of things that we, in theory, knew before, but probably didn't know to this level. That's okay. That's the way it's supposed to work. Now we're going to talk about some other things. And really what we're going to be talking about now is what happens with all those things that were weak. What can we know about them? And we can know a lot of things about them. So we'll talk about weak acids and acid ionization constants. We'll talk about weak bases and base ionization constants. We'll talk about the relationship between ionization constants for acids and their conjugate bases. Then we'll talk about buffers. Okay, because buffers are an important part of what falls out of all of this. So that's where we're going from. This is where all the math comes. Now, any acid that's not a strong acid is defined as a weak one. So for our generic HA, that breaks apart, it gives us an H plus and an A minus. So H plus, A minus. We get this K that's equal to the H plus times the A minus over the HA. And this is defined as a Ka because it's an acid dissociation constant. This is the same as the Ks that we talked about before. So we can list that as just K. I don't care that you put the A there. It's not important. You need to understand what it means when you see it. But I don't care that you list it. Okay. The value of pH is related to the value of the K. So the bigger the K is, the more H plus you're going to get out of that acid. Okay. So the more H plus I get, the lower the pH is going to be, and therefore the higher the pOH. So larger K values are stronger acids. Right? Now, in order for that to happen, the following conditions must exist or help in order for it to be a good acid. The bond between the H and the A must be weak. So A must be able to stand on its own once it's come off of that H. So that A must be able to handle that charge. Right? F, because it's so tiny, has a really hard time being an F minus. It's highly reactive. And so it doesn't handle being F minus by itself very well. So it will always react with things around it. And that's why HF is not a good acid. Now the HA bond must be polar, and the more polar, the better, because that makes it easier for that bond to break. Okay. Now again, HF, it is a really polar bond, but it's tiny, and so it's very difficult for that to pull apart. Okay. So those are things that we need, is for it to be stable on its own, to have that H come off, and it's perfectly fine, and it doesn't want to react with everything around it. Okay, so that's what we need out of our weak acids for this to be a decent weak acid. Okay. Now, if an acid or base is listed in the strong acids base list on, I think it's actually page 8, sorry, page 8 of the exam handout, it's then strong. If it's not listed there, you can assume that it's weak. Okay. Now there are tables on later on in this exam handout, and I'm going to minimize this if I can get my mouse to work. Come on. So, where is it? I can use it. So if you come down in the exam handouts, you'll find that there are some tables for weak acids and weak bases that are here. So this is some weak bases and their conjugate acids at 25 degrees on the bottom of page 12. And then we have some weak acids and their conjugate bases on page 13. Okay, so these things are here. They have K values for you, and that's because you'll need to work with those K values to be able to do some of the solving that we're going to be doing. So here's some weak acids and some additional weak bases that are listed here. We also have some for polyprotic acids. But just because you don't see it in that list doesn't mean it's not weak. Okay, so if it's not in that strong list, it is weak. Cool with that. Now, because I want to be able to solve for these values, right? Once I know that I can set this up using a K, then I want to be able to solve for those values. So just like we've done before, we're now going to be in a situation where we should be able to solve for the values of H plus, A minus, and the H, the HA that is left over. So that's what we're going to be talking about, is how do we do that using those K expressions that we have. So if I am looking at an acid, right, this is HF, and it breaks up to give me H plus and F minus. So that's the reaction that I have here, is HF breaks up to give me H plus and F minus. My initial concentration for HF is 5 times 10 to the minus first, so 0.5, right? Initially, I have 0 H and 0 F. Okay, so that's my initial. When we go through that change, every time I break down an HF, I have 1 X that comes out of that. That generates 1 H and 1 F. And that's the relationship between those things. And so at equilibrium, we'd be looking at that 0.5 minus the X, whatever's broken down, to give me X times X. But remember, we can assume that X is small. And so if we make that assumption, the expression that we end up with is that K is equal to that H plus times the F minus over the 0.50. Right? And again, that is a concentration, so that should go in like this. 0.5. Okay. Now I happen to know that Ka for this system is 7.1 times 10 to the minus 4. I got that from a table. Okay, so that's where I got that. And so if I know what that K is, then I should be able to solve this for H plus and F minus, right? And I would do that by multiplying both sides of this equation by 0.5. That leaves me with H plus is equal to F minus, which is equal to 7.1 times 10 to the minus 4th times 0.5. And of course, if I do that on my calculator, I have 7.1 second E negative 4 times 0.5, which gives me 3.55 times 10 to the minus 4th. I also know that at H plus and the F minus that I have here are both equal to X. And so I can put in X for this and X for this, and that's equal to 3.55 times 10 to the minus 4. And so X squared is equal to that value. And so I can find X by taking the square root. Okay. Now, I can take the square root of that. Second. And that gives me that X, which is equal to H plus, and F minus is equal to 0.0188 molar. Okay. Now, because we can always assume that X is small, we don't have to do this test. Then I don't need to use the quadratic. I don't have to do any of that, but it is possible to do that to see what is the more accurate value of this thing. So if you wanted to go through that math, that is perfectly fine, but it is not required. Okay. This value is my X, my H plus. It's equal to my F minus, and it's the value that would go in for equilibrium right here. So I have now used the Ka and the relationship between HF and H plus and F minus to solve for what that value is. Because I can take the negative log of the 0.0188, I could find the pH of this system. Right? That's not what I wanted to do. And that gives me that the pH equals 1.7. And I would lose one, so 1.7. Cool. So this is a fairly typical thing for us to look at is, okay, based on this initial concentration, what is the concentration of the acid going to be at equilibrium? That's a fairly common thing for us to solve for. One of the things that I hope you noted about this, and I don't know if you did or not, but when we set this K up, it's equal to X squared over the initial concentration of the acid. That's the way that this will work for all of these acids that we're going to look at, because we can always use these X is small. So anytime I go to solve for an H plus or an F minus in a situation like this, I can make that assumption. Does that make sense?
I do have a small question about the ice table.
Yes.
So when you have the products and then you have the reactants after that, is that why you have the plus X signs on the other side versus if like the situation was reversed and let's say it was H plus F minus, end result would be the HF, then the HF would be the X, but the H plus would be the negative X on the ice table. Is that right?
Correct. And because we know what the initial concentration is, we would end up with negative numbers when you do it. And it's not a big deal. You can do that. It's just a lot of people don't like what that looks like. So we never set it up that way.
Okay. Thank you.
Yes.
Mhm. And in this particular one, does it mean that the acid breaks down completely because the concentration of H plus is equals to the concentration of the F minus?
No. So that's not what that means. If it broke down completely, then your concentration of H plus at the end would be 0.5. And it's not. What
Oh,
it
okay.
means is that for every time you break down an HF, I have to get an H plus and an F minus. There's no other way for it to break down. So
Okay.
equal to each other unless there is another source of one of those things. That's always true.
Okay, and when you did the negative log of that number, you got the pH and because we're solving for H plus. Okay, it makes sense. Okay.
Yeah.
Because if it was a OH minus, then it would be POH.
Correct. That is correct. We'll get there, just not yet. So this is one way that we will look at this. Okay, so it could be that we have an initial concentration. We want to know what the H plus is or the F minus, either one, at equilibrium. Now, another way that you could see this is you could get some information about here's the initial concentration of this thing, here's the pH at equilibrium, what's the K value? So we could solve for that, and we should see that in a couple of slides. Okay, so this is not the only way that we're going to solve these using these rice tables. Now again, when we talk about our acids, as long as it's a monoprotic acid, it's going to look like this. If it's not, then we're going to have some more complications with that. And what happens, because there are different K values for each proton, so H2SO4 has two K values, one for the first H coming off. So H2SO4 looking like this. H plus the SO4 minus has one K value and a second K value for HSO4 minus going to H plus SO4 2 minus, because those are two different values. Oh, sorry. Then this setup would never work for an H2SO4 to just come apart to be SO4 minus. So does that make sense? And I won't ask you to solve for that because it's a two-step process.
Because there are two hydrogen, right?
Correct.
Present.
That's
okay.
correct. Yeah.
So it gives away two of them. So based on the definition, is that a proton donor twice, or does it
Yes.
only matter? Okay.
Yes. The first K value is strong for H2SO4. The second is not. So it is possible to do, here's what the concentration is after the first donation, and then find the concentration after the second donation, but it's complicated math. So I'm not going to ask you to do it.
Okay, and I do have just one weird question. So when you
Yes.
do the quadratic formula, you end up with two different values because it's a plus minus, that p square minus whatever the square root of that thing is.
Yes.
Like, so like would the pH always be it would be two different values for the pH for the X then, right?
No,
And
if you
like,
go through the math, what you'll find is that one of those values makes physical sense and the other one does not.
oh, okay,
Because
okay.
one actually gives you like an actual value, the other one is negative.
Okay.
So since I have a negative concentration, that doesn't make any sense.
Okay, that makes sense. Right. Thank you.
Yep. So other questions about this particular version of using the rice table for this. Now, of course, I have set up this rice table for you. Remember that it is your responsibility to set up the rice table if you're going to have to solve this yourself. Okay. So let's take a look at another one. So now we've got two situations that I want us to consider. One is for acetic acid, the Ka of 1.8 times 10 minus 5th. We want to know what is the pH of a solution of acetic acid that is 5.46 times 10 minus 4th molar. And then we have a situation for acetylsalicylic acid, which is actually aspirin, with a Ka of 3.0 times 10 minus 4. What's the pH of the solution of acetylsalicylic acid that is 6.38 times 10 minus 5th? Okay. So I'm going to walk you through the acetic acid one, and then I'm going to have you take a look at the one for acetylsalicylic acid. Okay. So I have my acetic acid. My formula is given to me, CH3COOH. I know that this will dissociate, and it will give me an H plus, because it's an acid, and then whatever's left over. That's CH3COO minus, because that's what's left. So those are the ions that I will get out of this from the acid that I started. I know that this will have a K that is equal to the concentration of the H plus times the concentration of the CH3COO minus over the concentration of the CH3COOH, and that is also equal to 1.8 times 10 to the minus fifth, because that's what the value is right here. If this is my reaction, then my initial conditions, it says that my initial condition is that the solution is 5.46 times 10 to the minus fourth. I assume that I have no H and no CH3COO minus. Okay. I know that when I go through the change, for every time I break one of these down, that's a minus X. Every X that I break down gives me an H and a CH3COO minus. And so at equilibrium, this would be 5.46 times 10 to the minus fourth minus X. This is X, and this is X. If this is small, then I can substitute into this K expression. I have 1.8 times 10 to the minus fifth is equal to X times X over 5.46 times 10 to the minus 4. Okay, so this is where I can start to solve. Now I know that X squared is going to be equal to 1.8 times 10 to the minus fifth times 5.46 times 10 to the minus fourth, multiplying both sides of the equation by this value. I can then do some math with that. And so I can take 1.8 second E negative 5 times 5.46 second E negative 4, and that's equal to this value right here. So X squared is equal to 9.8 times 10 to the minus 9th. And technically, I would report this as 9.83. And the reason for that is that since this is a constant, I can assume that it's infinitely well known, and therefore my sig fig should be limited by this concentration right here. Now, if that's the case, I can take the square root of both sides. Then my X would be equal to, and that's the wrong one. I did it again. I hate when I do that. It's too big. Here, it's much better. And that then gives me 9 point.
I think I got a different answer for it. I did the same thing in my calculator and I got a different answer.
Did you enter it exactly the same way?
Yeah, I did 1.8 e to the negative 5 over 5.46 e to the negative 4.
And you're
And
not dividing, it's a multiplication.
Oh, see, this is where I messed up.
I have a question.
Yes.
Sure.
So we do round the 9 point, we round it to 9.83 times 10 to the negative 9th, even though that's not like what the number that we're reporting. I thought we weren't supposed to round our sig figs like in the middle of like in the steps we're doing if it's not a number that we're reporting.
So I'm just writing that here. I did not do that when I did the math. So the math
Okay.
I used here what I had, but I wrote it down this way because that's the appropriate number of sig figs when I would write it.
Okay.
Does that make sense?
Yes.
And how do you take a square root of a negative number?
It's not a negative number.
Oh, it's just a very small.
It's very small. It's very small, yes. And so on my calculator, that is the second and the x squared button right here. That's the square root. So I hit second and the x squared, and that gives me the square root.
If you have a normal TI, you just do square root of the answer. That's perfect.
Correct.
Yeah. So 9.992 10 to the negative.
I would report that as 9.91 times 10 to the minus 5.
Oh, 91, yes, sorry. So
And so that would be my answer for H plus and my CH3COO minus. If I were asked what is the concentration of the CH3COOH, I would need to actually go through this math right here. So I would have to take the 5.46 times 10 to the minus 4th minus the 9.91 times 10 to the minus 5th. Now, it's not going to change it very much, but that is necessary. So I would take 5.46 second E negative 4, subtract the number that I calculated, and that's what I would report.
I guess what I'm struggling here with is because they're both x's, but they're not the same x's, you know, like as far as the value goes.
What do you mean? They are exactly the same value.
Because for the x, you would get 9.91 times 10 to the negative 5, right?
Yeah, and that's equal to the H plus
Right.
and the CH3OO minus. COO minus. So it's equal to this value right here and this value right here. This number, you have to subtract the x from it.
Well, that's what I'm saying. Like, why don't you need to subtract the same number for the H concentration, you know? That's what
Because
I'm saying. Like, that's what I'm struggling.
the H concentration is X.
But isn't CH3CO minus also X?
Yeah, but this is solving for CH3COOH, concentration of the acid, not the
Okay.
anion. So these two are equal right here to this. That is correct. But if you want to know the concentration of the acid, the CH3COOH, that's equal to this, because you have to subtract that value from your initial concentration.
Oh. Oh.
Because that's how
Right.
much it has dissociated.
That makes sense. Yep. Oh, because we are solving for CH3COOH, not the CH3COO minus. Okay.
Correct. Yes.
Gotcha. That
Because you
makes
may
sense.
get asked, what are the concentrations of everything at equilibrium? And in that case, while you've solved for H plus and CH3COO minus here, you have not solved for the CH3COOH.
So and
In order,
since the problem was of finding pH, you just do the negative log of that 9.91 number
correct.
times 10 to the negative
Yes.
5. Okay.
Yes. So we take the negative log of that, and that would then give me 4.
Okay.
So we're cool with that.
Mhm.
I guess I'm a little confused because I looked away for a moment to write it down. Where did that last bit come from with the negative log?
This is the pH, because it asked me what is the pH. That was the actual question, was what is the pH of the solution of acetic acid? So I'm taking the negative log of the H plus concentration, which is 9.91 times 10 minus fifth, and I get 4.0 when I do that.
Okay. So that's the actual answer, not the other one.
Well, because they asked me for pH, yes, that is the answer that they're looking for.
Okay. 1 second.
But yes, I have to do all of that work to get to it. So in a similar fashion, we want to do the same kind of thing for acetylsalicylic acid with a Ka of 3.0 times 10 to the minus 4 and an initial concentration of 6.38 times 10 to the minus 5. I'm going to give you 3 minutes to take a look at that. I'm going to leave this here so you can look and see what we did with this one and see if you can apply what we did here to this new question. And then we'll go through that in 3 minutes. Okay. Now, it says that I'm working with acetylsalicylic acid, which is C9H8O6, has a Ka of 3.0 times 10 to the minus fourth. I want to know what the pH of a solution of acetylsalicylic acid, that is 6.38 times 10 to the minus fifth mole. So I know that this is my acid. Now, there are two ways I can handle that acid. I can either say, okay, that C9H8O6 is going to break down and give me an H plus a C9H7O6 minus. Or I can call this an HA and know that it gives me an H plus an A minus. It doesn't really matter how you do that. It's entirely up to you. I wouldn't focus too much on making sure you get this to this right. I mean, yes, we've talked about the fact that the only difference between them is that proton. And so that's why I know that it just pulls off a proton and leaves whatever else is left. But again, I don't have to think about it that way if I don't want to. I can think about it in this generic sense because it gets me the exact same place. Okay, so either one will work. Now, that's my reaction. My initial conditions that I have are that this concentration is 6.38 times 10 to the minus fifth. I know that this one is 0 and this one is 0. Okay. I know that this is going to break down in a monoprotic fashion. So I'm going to take off one proton when I do this. So this is going to be a minus x. For every x that I take apart, I get 1x here and 1x here based on my stoichiometry. At equilibrium, I will have the 6.38 times 10 to the minus fifth minus that x, then x and x. So this looks exactly the same way that I had over here. Same idea, same kind of thing. I know that x is small, so I can ignore that portion as I do the initial solve. Now, remember that we have our k, which is 3.0 times 10 to the minus fourth. That's equal to x squared, x times x, over the initial concentration, 6.38 times 10 to the minus fifth. So I can multiply both sides of the equation by the 6.38 times 10 to the minus fifth. And I get that 3.0 times 10 to the minus fourth times 6.38 times 10 to the minus fifth is equal to x squared. Okay, so I can do that math. Take that 3.0 second e negative 4 times 6.38 second e 5. That gives me 1.1 or 1.914. Again, I would write that as 1.91 times 10 to the negative 8th is equal to x squared. Take the square root of both sides. That will give me that x is equal to 1.38 times 10 to the minus fourth. And again, that is the concentration of the H plus, and it's the concentration of that C9H7O6 minus. If I want the pH, which is what they asked me for, pH is equal to the negative log of that number right there, the 1.38 times 10 to the minus fourth. which gives me 3.8586. Actually, it's a pH, so 3.9. Sorry, I lose one again. 3.9 is my pH for that. And again, I'm not going to grade on the number of sig figs for that, so I worry about it, you don't. Okay. So that's where I end up with that number for my pH. Now, again, if I needed to solve for the concentration of an initial acid, C9H8O6 is going to be equal to the 6.38 times 10 to the minus fifth minus the 1.38 times 10 to the minus fourth. That gave me a negative number. That's weird. Why did that give me a negative number?
I got a different answer. I didn't get 1.91.
Cool. Awesome. I'm glad.
I got 1.89.
Okay, give me 2 seconds. Let me just, it'll bug me if I don't. I believe you. I just don't
Okay.
believe me. That's,
Okay.
trust me, it's all good. I'm trying to figure out why my calculator hates me. You got 1.89?
1.89.
I got a negative number
it's like
too.
-8.
So what is it that
Okay.
you? Let me see.
So I took my 3.0.
I also got.
Go ahead.
I also got the same. I got the same number you did, the negative number. So what did you do differently to get the? Sorry, I'm just trying to look at the calculator.
No, you mean what did I do differently? I think you and I
Yeah,
did
to
the
get the
same thing.
1.94 instead of the negative number.
Oh, yeah. Because I'm not sure. If I multiply those two numbers together, the 3.0 times 10 to the minus fourth times the 6.38 times 10 to the minus fifth, I end up with 1.914 times 10 to the minus eighth. And if I take the square root of that, that should be 10 to the minus fourth, which of course gives you a negative number, but I'm not sure how.
I got the same numbers, and then for the concentration of that, I got negative 7.48 times 10 to the negative 5. Did you get the same one?
No, I did not. So what'd you do?
So my
I love
pH
it
was the
when
same as yours. The x value was exactly the same. The x squared was all the same. And then I did 6.38 times 10 to the negative 5 minus 1.38 times 10 to the negative 4, and I got negative 7.42 times 10 to the negative 5.
yeah, but it shouldn't be a negative number.
Yeah.
That doesn't make sense. But we all did the same work.
Yep.
I'm guessing here.
So where is this 1.914 times 10 to the negative 8 coming from?
It's the 3.0 times 10 to the minus fourth times 6.38 times 10 to the minus fifth.
Okay.
I actually got a positive for mine now that I did the calculations. What I got was, so like the x2 thing, and once we squared it, I got the 1.89 to the negative like 8. Then once I kept going, I eventually instead got 1.37 10 to the negative 4 instead of that negative. And all of mine were positive.
We ended up with the negative once we got to the subtraction right here. So it's when we were solving for the concentration of the C9H8O6. Did you do that part?
Yeah, I did that. Um, I mean, I don't know.
I love it. We can't share. It's great. So you got your x to be 1.89 times 10 to the minus fourth too.
Can you say that again?
Your x value was 1.89 times 10 to the minus fourth. Is that correct?
Yeah. Yes, but it was to the negative 8. And then whenever I kept doing it, yeah. Because I mean, for the pH, I got like 3.86, which is like
That's exactly
low.
the same. That's the right number. You
Yeah.
just rounded up to 3.9.
Okay. Thanks.
How do you get a 3.86 if you have a different x factor? Because it's like a negative log of that number.
Wait,
This
negative log of this? The
she got the same
1.38.
she got the same pH, you know, but she had a different x factor. So like I feel like
Yeah,
how
but
can you get the same number if it's just a negative log of the x?
if I understand correctly, then if it was 1.89 times 10 to the minus 8, that the x squared portion, when you take the square root of that, then you would end up with 0.01374 instead of 138. And so if you take the negative log of that, (1.86), which is what was reported.
Mm-hmm. Right.
Correct.
Well, so what's correct?
Well, so here's the thing. It should not be a negative number. Whenever you run into a negative number like that, that means that there's a mistake somewhere. And I'm trying to figure out what the mistake is. Now, it could be that the value that was put in for the initial concentration was not sufficient. Now, that happens because if you don't have enough acid, then it can't dissociate the way it's supposed to. So that may be what I'm looking at here. I will have to check.
But on the test, we're not going to run into this, right?
No, I will have worked these 8 million times. So
Okay, perfect. Thank you. Sorry, this was just like
no,
a lot.
and I completely understand. It's the, well, what am I supposed to do if I run into this? Yeah. So I'm trying, because I cannot find a place where we've done the math wrong. So I understand that
and we all got the same answer. Well, I at least
right.
got, like the correct pH and the correct X value. So I don't know. Yeah.
So
Just like the
correct.
solving for the
Right.
what is it, the
I
equilibrium
did
for
totally get
the
it. Like, I got the same one too.
method.
So yeah, I mean,
Okay.
again, this is a problem on the problem end, which is not your fault, my fault. We did the solve the way that we're supposed to, and I found no errors in the math that we did. So what we've done is correct. how I set it up is the problem here, and I will get back to you about what was wrong with it. Does that sound acceptable?
Yes, thank you.
And that way we can move on and not worry about it for now. So, cool with that.
Yep.
So let's take a look. We want to solve for POH this time. And all we're going to do is solve for POH. That's all I care about. So for these two scenarios, I figure I should do one, and then we'll work the other. I have you guys take a look at the other one too. Okay. So phenol is a weak acid with a Ka of 1.3 times 10 to the minus 10th. If that is the case, then what's the pH of a solution of phenol that's 3.26 times 10 to the minus 6? So C6H5OH. It's a weak acid. That means it is a proton donor. C6H5O minus plus that H plus. I know that that's what I'm looking at because it is an acid. So I have a situation where that's what I'm going to be looking at. If that's my reaction, my initial conditions, I have 3.26 times 10 to the minus 6th, 0, and 0. My change, again, because I'm only losing one of these, for every time this breaks down, I get one of these and one of these, which leaves you with an equilibrium of 3.26 times 10 to the minus 6 minus x, x, and x. My K expression is equal to 1.3 times 10 to the minus 10th. That's equal to x squared over 3.26 times 10 to the minus 6. So multiplying both sides by the 3.26 times 10 to the minus 6. And so 1.3 times 10 to the minus 10th times 3.26 times 10 to the minus 6 is equal to x squared. Oh, I changed. Oops. So x squared is equal to 4.238, and I'm not going to round anything at this point. 10 to the minus 16. X is therefore the square root of that. Gives me 2.0. It's 10 to the minus 8. And if that's my
round it
x,
up to 2. You wouldn't round it up to 2.1.
so actually, yes, you are correct.
I did have this is sort of a side note about the post lab equilibrium.
Yes.
There was one that like I originally like got wrong because it was like I think like 1.8, they rounded it down to 1.84 and I kept getting 1.85 because like there was a 5 after it. So like I was rounding up, but they were rounding down.
After
from a
class, we can talk
Okay,
about
yeah.
that. It's
Okay.
because, did it end in 5.5? Was that the last part of it?
I think so, but I'd have to go back and look at my work.
Yeah, so it's because it's a 5.5, it's because it ends in 5, and therefore you have to look at the number before it to decide whether you round up or down.
Okay, thank you.
Yeah, so we'll talk about it after class though. Because I totally get that, and I can give you those points back. It's not, because it's very rare that happens. So if this is my x, that's equal to my h plus. And so if I want POH, I can take the negative log of the 2.1 times 10 to the minus 8th. Which gives me 7.7. And then my POH is going to be equal to 14 minus that value. Which is 6.3. So that is what I would report. Now, why did I show you this? Because sometimes we ask for POH as opposed to pH. Why? It depends on what we're doing. So there are some reasons that we would need to do that, but make sure that you're reading the question, RTFQ. So make sure you read the question that was asked and provide the answer that was asked for. Okay. So questions about our process there. Looks very similar to what we've done before. So why don't we try this for the hydrocyanic acid? I'll give you a couple of minutes to work on that. Okay. So let's talk about hydrocyanic acid, which is HCN. HCN is going to break down and give me an H plus and a CN minus. That's my reaction. My initial condition for this is that I have 4.91 times 10 to the minus 1 molar of hydrocyanic acid. I initially have 0 of the H and 0 of the CN. I know that when I do my change, every time I break down one of these, I get one of those and one of those. So I end up with 1 H plus and 1 CN minus for every HCN that I've broken down. And at equilibrium, I have 4.91 times 10 to the minus 1 minus X, X, and X. X being small, we can ignore that. And so I end up with a K that's equal to 4.9 times 10 to the minus 10th equal to X squared over 4.91 times 10 to the minus 1. And so my X squared is equal to that 4.9 second EE minus 10 times 4.91 second EE to the minus 1. And that gives me 2.4059 times 10 to the minus 10th is equal to X squared. And so my X being the square root of both of those. Gives me 1.55 times 10 to the minus 5th. And again, that's equal to my H plus. If that's equal to the H plus, I can take the negative log of that number to give me my pH. And that's equal to 4.8. And then my pOH is equal to 14 minus the 4.8, which is equal to 12.2. Cool with that.
I got 9.2.
So did
Oh
I.
yeah, I can't do math. I told you I shouldn't do this without a calculator. Thank you. There's a reason I never do this without my calculator. So cool with that. And what we've seen so far, everything that we've looked at so far, has been based on weak acid dissociation. The next thing we need to talk about is our weak bases. And that's a slightly different scenario. So let's take a look at what that looks like and see what we do with that. Now, any base that's not a strong base is a weak one. So it can react with water, generally speaking, to pick up a proton and leave us with an OH minus. Now, there are situations where we talk about generating OH directly, but that's typically for a strong base. This is the behavior that we typically see for our weak bases. So that's why we're looking at this scenario. So we have our base B plus H2O giving me BH plus an OH minus, which then gives me this KB is equal to BH plus times OH minus over the concentration of B. The value of pH is related to that value of K. Here we're looking more directly at the pOH versus the value of K. Okay. So the more the reaction favors making OH minus, the lower the POH will be, and therefore the higher the pH. Okay, so larger K values are stronger, and actually that should say bases. So larger K values, again, stronger bases. In order for that to happen, following conditions must either exist or help. Again, weak bond between M and the OH, if that's the way you're generating it. You must have and that's M for metal, by the way. You must have a stable BH plus. Okay, so once you've added that proton to it, it needs to be stable. Okay, and if we're talking about taking the OH off, the metal must be stable on its own. And if we're adding an H to it, then we want that BH plus to be more stable than the B on its own. Okay, so either of those situations is favorable. Okay, so cool with that. All right. So if that's the situation that we're looking at, then we have very similar scenarios for solving information about the weak bases. We can again generate a Rice table for a base equilibrium. Okay, so in this case, we are dealing with NH3, right, which we know is a weak base, added to H2O, which is a liquid, so it doesn't appear in this. We then get the NH4 plus, that should have a 4 right there, and an OH minus. Okay, if that is the scenario that we're looking at, and we're looking at a 0.5 molar NH3, so very similar to what we talked about for our initial acid, then we have a situation where every time we have one of these that breaks down, okay, we get a negative here to generate a positive here. Okay, so we get a +1 here and a +1 here. We end up with our 0.5 minus X for our NH3 and our X and our X here. Now, if that KB is equal to 1.8 times 10 to the minus fifth, which it happens to be, then 1.8 times 10 to the minus fifth is equal to that X squared of the 0.5. And this looks really familiar because again, we're going to ignore this because it's small and therefore we have that X squared over 0.5. And this is actually something that we've looked at previously. So we take that 1.8 times 10 to the minus fifth, multiply it by the 0.5, that's equal to X squared. Do that happy math, and that gives me 9.0 times 10 to the minus 6 is equal to X squared. I take the square root of both sides. And that gives me X is equal to 0.003. Okay. If I were looking for the concentration of the NH4 plus, that is what that is. It's also equal to the OH minus. If I wanted to find the NH3, that would be 0.50 minus the 0.003. Mm, 0.497 molar, which technically would round up to 5. So, if we were doing it to the correct number of sig figs, we'd never even see the difference. Okay. Which is why we mean that X is small comparative to that. And if we wanted to find a pH, then we could take the negative log of the 0.003 to find the POH. And that gives me 2.5. And 14 minus that. Which is 11.5. So, cool with how we set that up, what we did there. The scenarios between our H3O plus and our Ka and our Kb are very, very similar. So we work through all the exact same things between these when we talk about things. Okay. So questions about. Go
I
ahead.
do have a question. So the stoichiometrically speaking, like, does that, so you missing an H somewhere, or does it matter there in that reaction or no?
We have NH3 plus the H2O. Gives me an NH4 plus. We've taken one of the protons off of the water.
Oh, right. Wait, okay, never mind. Okay.
It wasn't
see.
balanced without the 4. That is very true. But
Okay. So that's why I was like, all right.
yeah, it was missing before that. That's correct.
That makes sense.
So cool with that. So again, in my head, it becomes a big question of, is it an acid and therefore generating an H plus, or is it a base and therefore generating an OH minus? Because that will determine whether we're, solving for pH or POH, depending on what we're doing. Okay? But the math works exactly the same. So we can go through some examples for methylamine and caffeine, both of which are weak bases. I'll walk through the methylamine. I'll give you a minute to deal with the caffeine one, and then we'll come back. So let's talk about methylamine first. So methylamine, CH2NH2. We'll react that with an H2O. That will then generate a CH2NH3 plus an OH minus. So taking a proton off of here, adding it to the species to give me that. Okay. Now again, since water is a liquid, it does not appear in this. We don't care about it at all. This is my R, this is my I, my C, and my E. My initial condition for my methylamine is 4.37 times 10 to the minus 2. So that's my initial concentration for that. I'm assuming I have none of this and none of this. Okay. Every time I take and react one of these, I take one of those out of there to generate this. And I generate one of these as well. Okay. So at equilibrium, we're looking at 4.37 times 10 to the minus 2 minus x. X is small, so I can ignore it. X and x. My Kb is equal to 4.4 times 10 to the minus 4th. That's given to me right here. And that's equal to x squared over 4.37 times 10 to the minus 2. I can multiply 4.37 times 10 to the minus 2 by both sides. So 4.4 times 10 to the minus 4th times 4.37 times 10 to the minus 2 is equal to x squared. Oh, there you go. 4.4 second E negative 4 times 4.37 0.37 second e negative 2 gives me 1.9228 times 10 to the minus fifth. Take the square root of both sides. And that gives me 0.0043. Okay, and that again is equal to the OH minus or the CH2 NH3 plus. And so my POH is equal to the negative log of that value. And that gives me 2.4. So questions about that? So I'll give you a couple of minutes to look at the caffeine one, and then we'll come back and see what we get for that. So I went ahead and set up my rice table with my caffeine C8H10N4O2 plus an H2O. Picks up a proton to give me C8H10N4O2H plus an OH minus. I put in my initial concentration for that caffeine, which is 6.52 times 10 to the minus 2. I know that every time I break one of those down, I end up with a C8H10N4O2H plus and an OH minus. And therefore, I end up with this 6.52 times 10 to the minus 2 minus X, but the X is small, so I'll ignore it from now, and then an X and an X. I can then plug that into my KB expression, which has a value of 5.3 times 10 to the minus 14th. So that's equal to X squared over 6.52 times 10 to the minus 2. I can multiply both sides by 6.52 times 10 to the minus 2 to give me this expression right here, and that's equal to X squared. X is then equal to the square root of 3.4556 times 10 to the minus 15th, which is what I got when I multiplied these two numbers together. And therefore my X is equal to 5.9 times 10 to the minus 8. And that, of course, is equal to the OH minus concentration. So if I wanted a POH, that's equal to the negative log of that value. And that gives me 7.2. Now, does that make sense?
It does. I do have a question with the formula writing.
Yes.
When you do that whole reaction with a weak base,
Yes.
does it matter where you put that H proton? Like for instance, you have that at the end of the formula. I had like the same thing, but like, can you just add that to the total number of the hydrogens there, or no? Like, can you
Can
write it
you?
as a C8H11 NH N4O2? I don't know.
Yes, absolutely you can. It does not
Okay.
really matter where you put it. The only reason I put it at the end is to emphasize that we added a proton to it to show that it's acted as a base. That's
Okay.
it.
So okay, so if I write it on the test, like you would accept that answer as
As
like
long as there's
I was doing the same thing. Like I feel like for me that makes more sense. So because like I
yeah.
can see that proton at the end.
No, I mean as long as there's another proton and a positive charge, I don't care where it ends up. It doesn't really matter because two different chemists will write it two different ways.
Okay.
Now, is everybody comfortable with the acid side and the base side? Because again, the math is very similar. Now, there is another thing that I've done here where instead of asking for POH, I'm asking for pH. I do intend to post this because I'd like to talk briefly, and I mean briefly, about the next point in this before we, without worrying about this part, because I feel like, and it's probably just me, this is highly repetitive. And we've been doing the same calculation over and over and over again. And I'm hoping that you feel the same way. So
Totally.
we'll need to look at this right this second, but I will definitely post this so that you guys can see it. Now, the next thing I want to talk about, and it's important before we start talking about buffers, which we'll get to the next time, is that there's a relationship between Ka and Kb. So if we consider the reaction with acetic acid, CH3COOH, and that breaks down to give me an H plus and a CH3COO minus. We've been talking about that. That's the reaction for the acetate ion. And that gives me this K. But the acetate ion also reacts with water in this reaction right here to give you back that CH3COOH and an OH minus, right? And that has this Kb, where I have CH3COOH CH times OH minus over CH3COO minus. Interesting thing happens. If I multiply Ka, this expression right here, times Kb, this expression right here, which I've done right here. So this is the Ka portion. This is the Kb portion. This cancels with this cancels with this, and I'm left with H plus times OH minus, which equals Kw. So if I take the K for an acid and I multiply it by the K for its conjugate base, then they are related through Kw. Okay. What this implies, and may not be as obvious, is that if I know Kw and I know Ka, then I can solve for Kb. Or if I know Kw and I know Kb, I can solve for Ka. That is
But
true.
isn't KW like a constant though? Like we know the number.
Yes, it's 1 times 10 to the minus 14th at 25 degrees. That is correct. So as long as you know what this value is for Kw, which you do, and you can find a value for Ka, then you can get a numeric value for Kb, or vice versa. And it's important to understand that because the tables that you have available don't always have exactly what you need. You may need a Ka, but you only have the Kb. So you can find it if you have the Kw, and you do. So you can always solve for the other value. Okay. Now, does that make sense? So for instance, when we talked about NH3, the Kb for NH3 was equal to 1.8 times 10 to the minus 5th. But if I needed to know what the Ka was for NH4 plus, I wouldn't find that tabulated anywhere, but I might need to know what its value is at some point. That might be necessary. And so what I could do is I could take 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5th, and that will give me the Ka for NH4 plus. Okay, so that's exactly how that kind of thing can work. We can solve for the other value if we need to. Okay. So this is something you'll get some practice with. Alex will ask you a bunch of questions about this. There is some practice in here as well. I've got some values right here. So look, acetic acid is a weak acid with a Ka of 1.8 times 10 to the minus 5th. Ammonia is a weak base with a Kb of 1.8 times 10 to the minus 5th. So we can solve for the opposites of that by taking and doing 1 times 10 to the minus 14th divided by those values. And of course, I could do that at least once. So 1 second EE negative 14 divided by 1.8 second EE negative 5th. And that gives me 5.55 times 10 to the minus 10. And technically, I should report this as 5.6. It should have the same number of sig figs as what I started with. And I could do the same for these two values right here. Does that make sense?
Are there any unit to this number, or is just 5.6 times 10 to the negative 10? Or is it more?
Again, with our Ks, we typically don't worry about the units, so I wouldn't worry about it. I'm not going to be looking at that. You at worst, you're going to get a true false question. I'll ask you what the units of K are.
And the answer is no units.
Well, I mean, technically, it depends on what the expression of K is. So if my Ka is equal to H plus times A minus over HA, and all of these are in units of molarity, then my Ka would have units of molarity for that expression, but it will depend on what the expression is, what those units will be.
Well,
So
like for
you,
instance, you had earlier in your slide, you had that like the rice table or whatever, and it said, you know, like the H plus or F minus, whatever. It was in molarity. So if you put it on a chart, do we follow up with the units or?
I mean, you're not expected to put the units on the chart. That's not required. It's absolutely
Okay.
not required. I only show them to you because it's important that you understand that they have units of molarity, i.e., if we're doing math with it, it has to be in molarity. So that's important.
Gotcha.
But again, you might get an expression like this and you might get asked what's the unit on this one. But that's going to be different than something like the reverse of this, where we would have HA over H plus times A minus, because that would be 1 over molarity. So it's always dependent on what that expression is. And again, the logic is the same there. If each of these are molar units, then this one would cancel with that one, and you'd have 1 over M here and M here. So that's why I say that. It's always dependent on what we're looking at.
Makes sense. Okay.
And if one of them is squared, then it's molarity squared, you know, that kind of thing. So there's no definable unit without looking at the actual expression.
Sounds good.
So this is where I intend to pick up on Wednesday. And again, depending on how things go Wednesday, we will either be completely ready for the test or we will push it out a bit. And again, if I push it out, then it will open on the same date. You guys should have plenty of time to get to all of that information. Well, okay, I think you will, but I will extend the due date if that is necessary. Okay.
Yes, ma'am. Hold on. So when does the test due? Friday?
So
Wednesday?
on Monday.
Ooh,
So
on
it
Monday.
starts on Friday, which is the
Okay.
27th. Where's my calendar?
You just basically want to have the test done before the next class after whatever Friday lecture.
Yes. So,
Okay.
I mean, the test opens on the 27th, so you can start it that day. But we will technically have no class on Monday, technically, so that you will have time to take your test if you haven't taken it yet. That is the official exam date. But I have opened the exam over the weekend for people who may need some more time, some, you know, a slightly more flexible schedule. So that's typically the way I'll handle it, is it'll open the weekend before whenever it's due.
Okay. I think that sounds good. Sweet.
Okay.
Bye.
I found
Yes.
I found the I think I found the question where I got it was 1.8450 and they rounded it down. I'm not sure, like I can't go back and look at the quiz anymore on Alex. I feel like I might have just since I got 2 attempts on the quiz. I think
Yeah.
on my second attempt I just put 1.84, so I think it might have given me the point. But I did want to ask you, like that should be rounded up, right?
Well, so because it ends at 0 and the
Okay.
number before it is odd, then it stays.
So it is 1.84.
Okay, can you say that again about the oddity of the
Wait,
numbers?
where are we rounding it to? Is the one point? Are we talking about
It was rounded to
1.84 versus
1.84.
okay? So because an X, and that is that, and so that is so my rules state. Where are my rules? Come on, where is it? This comes up so seldom. Where did I put it? Is it not here? No, of course not. That's what I want. If the digit immediately to the right of the last significant figure you want to retain is 5, followed by any non-zero digit, 5, not followed by any non-zero digit, and preceded by an odd digit, then you increase the last digit by 1. If it is 5, not followed by any non-zero digits, and the preceding significant digit is even, do not change the last digit. That's where this comes from.
So since the 8 is even, or wait, yeah,
Yes.
since the 8
Now
is
it-
even,
Well, so it was 1.8450, right?
yes.
And we were trying to round to the second place. Yep.
Yes.
Sorry, you can't see what I'm writing. So yes, because the 8 is even, that's why it stays. It's
And
a
that's only
really
because it's 5. So if it was 1.8460, it would round up.
correct. The only
Okay.
time that this applies is when it's the next thing is a 5 and then it's a 0 right after it.
Okay.
That's the only time it applies. It's a really weird thing. So, and it's just because we can't always do the same thing. We can't always go up or down. We have to have sometimes where we go up and sometimes where we go down.
Yeah. Okay.
Weird thing, I know. But I will check your answer and see, because if you didn't get the points, I'll give it back to you because I
Okay, thank
hate
you.
when it answers like that. So
Thank you very much.
yeah, no problem.